Thank you for having me today. I'm going to talk about some joint work with Jenna Rachgott and Anna Wygant, in which we use the combinatorics of Grothendieck polynomials to get nice, succinct combinatorial formulas for this algebraic invariant of Castelnuovo-Mumford regularity for certain generalized determinantal ideals. And to start out with, we'll just talk about Schubert varieties and these Kazhdan-Lusztig varieties. And for that, we'll start with the complete flag variety. So we take all of the chains of complete flags from 0 to Cn, where at every space in the chain, for every consecutive subspaces, I want the dimension to go up by 1. And so that'll give me our complete flags. And we can identify this variety with GLN, those n by n invertible matrices with complex valued entries, mod the Borel subgroup. So those are those upper triangular matrices in GLN. And this Borel is going to act on our complete flag variety with finitely many orbits. And those orbits, we'll call those our Schubert varieties. And the Zariski closures of those orbits, the orbits are our Schubert cells, and the closures of those orbits give us our Schubert varieties. I think I misspoke for a second. And in 2006, Woo and Yong were interested in studying the singularities of these Schubert varieties. And so in their study of these singularities, it happens that they could restrict their focus to just looking at local neighborhoods of these Schubert varieties, just looking at neighborhoods of these Schubert varieties at torus fixed points. And so that's what this intersection is just some local neighborhood of a torus fixed point. And due to a theorem of Kazhdan-Lusztig, in fact, this neighborhood is isomorphic to taking your original Schubert variety and instead intersecting it with an opposite Schubert cell with this extra factor of affine space just hanging off the end. And so they said, well, maybe we'll just knock off that factor of affine space and study what's left over and call that the Kazhdan-Lusztig variety. And these Kazhdan-Lusztig varieties have very explicit descriptions. These are generalizations of those matrix Schubert varieties that Alan was talking about earlier. These are generalized determinantal varieties, so they're cut out by some determinantal conditions. And these defining ideals are very explicit. So just to give you an idea of the sort of what these look like, I'll just briefly go through an example here of one of these defining ideals. So in this case, we'll always have our Kazhdan-Lusztig varieties indexed by 2 permutations V and W. And we'll always have that V is going to be greater than or equal to W in Bruchal order due to the geometric story that we all started out with. And what this permutation W is going to tell us is that's going to tell you about the ranks of the minors that we'll be taking to build our generators for our defining ideal. And this permutation V is going to tell us how to build the matrix that we're actually taking these minors of for our generators. And throughout this talk, one combinatorial object that we'll be using repeatedly is the Rotha diagram for our permutation. All of our permutations today will be in one-line notation, and you build the Rotha diagram by looking at your permutation in one-line notation and putting one of these bullets in row I, column WI. So 1 gets sent to 4 by W, so in row 1, column 4, I'll put a bullet. 2 gets sent to 1, so in row 2, column 1, that'll get a bullet, and so on. And then south and east of each of these bullets, I want to scratch out all of the integer points immediately south and east of those bullets. And every integer point in this n by n grid that survives this process, it hasn't seen any action, those will get these boxes. And this collection of boxes is what we call the Rotha diagram of our permutation. And one thing you can extract from just looking at this diagram is you can write down, for example, the rank matrix of your permutation. There's a lot of different ways that you can do this, but one way you can see it from the Rotha diagram picture is you can pick whatever value of the rank matrix you want to compute, find the corresponding entry in or corresponding position in this diagram, and you just look northwest And in this position, you're just going to store the number of bullets that you see when you're looking northwest of this position. So here, if I'm looking northwest, I could see this bullet and this bullet, that's 2, so that's why we store a 2 there. Okay, so this rank matrix that's defined by W is going to dictate the size of minors we take. And how we figure out the matrix that we're taking our minors of is essentially just hiding in, again, the Rotha diagram for V instead. So anywhere that, any position in this matrix that would be in the Rotha diagram for V, that's going to get an indeterminate Zij. Anywhere that would have seen a bullet gets a 1. And anywhere that would have seen one of these sort of death rays, that gets one of those zeros. And so by taking the minors of this matrix according to, taking northwest minors according to these ranks here, that's how we get our generators that cut out our defining ideal. And if you're more familiar with matrix Schubert varieties, they're defined in a very similar way, except the minors that you're taking in the matrix of, the matrix is going to be all Zij's. So you can sort of figure out how this is a more general version of that, and you can actually recover those matrix Schubert varieties from this setting. And you can also recover your classical determinantal varieties from this setup. And we can do a lot of things with these varieties. So we can compute its minimal free resolution, for example. And things that you can extract from this minimal free resolution is, one thing you could write down is its K polynomial, where this K polynomial is a Leroy polynomial where your coefficients are going to be alternating sums of Betty numbers. Another way that you might have seen the K polynomial pop up is as the numerator of the Hilbert series, for example. And another thing that you could try to compute is the Castelnuovo-Mumford regularity of your coordinate ring. So here, this regularity, you can read it off from the minimal free resolution as just being the maximal difference of indices of the non-vanishing Betty numbers here. And what this tells us sort of roughly is how complicated our coordinate ring is, because it can give you an idea of course, how complicated your minimal free resolution is and so on and so forth. So if I want to get sort of maybe a rough idea as to how complicated things are going to be with this coordinate ring that I've picked up, maybe I want an easy test for what this regularity is. But if I am not sure how complicated my coordinate ring is, maybe I don't want to have to write down the minimal free resolution of this coordinate ring to actually get this check. So we'd like an easier way to compute this regularity. And in fact, when our coordinate ring is Cohen-Macaulay, we have such a nicer way to do things. So in the setting where we are Cohen-Macaulay, this regularity can be computed by just taking the degree of your K polynomial and subtracting off the codimension of your ideal. And for now, I'm just going to restrict to that special case of matrix Schubert varieties inside of our world of Kazhdan-Lusztig varieties. And in that setting, we have that these matrix Schubert varieties are Cohen-Macaulay. In fact, all of our Kazhdan-Lusztig varieties are Cohen-Macaulay. So we can apply this theorem to hopefully get an easier way to compute these regularities. So we know that they're Cohen-Macaulay, these matrix Schubert varieties. So according to that theorem I had on the previous slide, we should have that the regularity can be computed by taking the degree of the K polynomial and subtracting off its codimension. So due to a theorem of Fulton in his paper in which he introduced these matrix Schubert varieties, we know that the codimension is just the Coxeter length of our permutation. And this Coxeter length is very easy to compute. It's just you sum up all of the inversions in your permutation and you're good to go. So that's great to hear. What about this piece? So the K polynomial of your matrix Schubert varieties are these Grothendieck polynomials. And these Grothendieck polynomials are the K-theoretic versions of the Schubert polynomials that Alan was talking about in his talk, although he was talking about the double version, but it doesn't matter so much for what we're talking about right now. But so these Grothendieck polynomials are a K-theoretic version of those Schubert polynomials. So that tells us that the Schubert polynomials that he was discussing are the lowest degree terms inside of our Grothendieck polynomial. So these Grothendieck polynomials will often be inhomogeneous, and they have a lot of nice combinatorial rules that allow us to compute them. So again, that gives us some hope that we should be able to actually compute these degrees combinatorially. However, the formulas that we do have to compute these polynomials can be a bit involved. So they involve, again, from Alan's talk, maybe these bumpless pipe dreams and things like that, where you want to maximize the number of pluses, for example. And that can be sort of hard to do on its face. So we were hoping to find a more simple formula for these degrees to in turn get a nicer formula for these regularities, for these matrix Schubert varieties. And for today, I'm going to tell you about our theorem, which allows us to compute the degrees for the vexillary case. But stay tuned, because on Sunday, Oliver is going to tell us about a general formula for the degrees for any Grothendieck polynomial, for any permutation. But right now, we'll just talk about the vexillary case. So for vexillary Grothendieck polynomials, this vexillary means that my permutations are all going to be 2, 1, 4, 3 avoiding. And I'm just going to tell you about how our theorem works through an example. But just to sketch, hiding inside of my degree of this polynomial, I'm going to have that Coxeter length hanging out. And it'll be some sum of anti-diagonals of a particular partition. So that's the short version. And how it really works is we'll start off with our tried and true Rotha diagram for our permutation V. And inside of each box of my Rotha diagram, I'm going to store the rank. So for example, here, this box here, if I look northwest, I see 1 bullet, so I get a 1 in that box. And personally, I love to work with Tableau, so let's just shove all of the boxes northwest along diagonals to get something that looks like a partition shape. So I have a Tableau here where, again, I'm just storing those same ranks that I had from my Rotha diagram. And so what our formula says to do is we have our Coxeter length of our permutation, which you can also read off from these diagrams. It's just the number of boxes in your Rotha diagram is the Coxeter length. So that's 12 here. And for the rest of these extra terms that will contribute to our degree, we're just going to do an iterative process from 1 to n. So here from 1 to 7. And we'll start with I equals 1 step. So for I equals 1, I'm just going to highlight the subset of this Tableau that has entries greater than or equal to 1. So that's that subset. And I just want to mark out the longest anti-diagonal path in this subset. And so by anti-diagonal path, I want to form an anti-diagonal of boxes such that no 2 boxes are directly on top of each other, nor directly next to each other. And so the longest path that I can get is of length 3, so that's going to give me that 3. So that's my I equals 1 step. What about I equals 2? We'll do the same thing. So I highlight the subset that's greater than or equal to 2. I only have 1 box, so my longest path is going to have length 1. So that's going to contribute this 1. And if I do this for any I greater than 2, there's obviously nothing in my Tableau that has entry greater than 2, so those will all be trivial. So actually we're finished, and the degree of this Grothendieck polynomial would have been 16. So this gives a not so complicated way to write things down, just writing down your Rotha diagram, filling in ranks, that's easy to do, and then just measuring anti-diagonals. And thankfully that codimension was already hanging out in our degree formula. So combining our formula from before that the regularity should be this degree of our Grothendieck minus that codimension, it tells us that we are really measuring the regularity by precisely counting those anti-diagonal paths. That's really capturing these regularities. So in the previous example, the regularity was 4, because 4 was the sum of all of those anti-diagonal lengths. Okay. And now we'll sort of branch out a bit more. and go back to our Kazhdan-Lusztig varieties. So if we consider our Kazhdan-Lusztig varieties where the V and W that are indexing our varieties are Grassmannian. So whenever I'm writing down my permutation in one-line notation, I want the sort of entries to decrease at a unique point in my permutation. So if I'm just considering our Kazhdan-Lusztig varieties indexed by a pair of Grassmannian permutations where they sort of drop at the same point, respectively, then in fact, our Kazhdan-Lusztig variety is going to be isomorphic to a vexillary matrix Schubert variety, which tells us that we can use our formula of these anti-diagonals to, again, compute the regularity for these Kazhdan-Lusztig varieties that are indexed by these Grassmannians. But one thing that we should make sure is the whole point of this was making sure that doing all of these computations are as easy as possible. So I should hope that the map from this Grassmannian pair to this vexillary permutation, that should better be pretty simple. Otherwise, this isn't very useful. But luckily, the map is pretty straightforward. So one beautiful thing about Grassmannian permutations is once you fix the symmetric group that they're living in, they uniquely correspond with partitions, integer partitions. And so what we can do is just draw the partition that's corresponding to our smaller Grassmannian permutation sitting inside of the partition that's corresponding to that bigger permutation. And we'll use the combinatorics of something called excited Young diagrams, which is just some local moves on these subsquares where I'm allowed to do this local move as much as I want. And so if I do that on this diagram here, so that all of the gray boxes sort of flow southeast as much as possible according to this rule, then I'll actually just be able to read off the Rotha diagram for V from that final southeastmost diagram. And so that's how you can read off your V. So that's how we can, again, measure this regularity for this Kazhdan-Lusztig indexed by these Grassmannians. Right? And we can apply this theorem in a couple of different ways. So in 2015, Kumini, Lakshmi Bai, Shashri, Shashadri were writing down certain free resolutions of a particular variety where they build this variety by taking a Grassmannian Schubert variety, intersecting it with the opposite big cell, and then looking at the fiber, the restriction of the fiber in this space of matrices here that have this particular block form. But anyway, so they had these YW that are just these Grassmannian Schubert varieties intersected with this opposite big cell. And they were interested in these free resolutions. And in particular, they had a conjecture about what their regularities were when they put certain extra conditions on the permutations. One thing I should note is if they actually have a theorem in their paper about actually computing these free resolutions, so why shouldn't they actually know what these regularities are? But in fact, their free resolutions were sort of had some additional computations hidden inside of computing cohomology groups. So it wasn't obvious from looking at the formulas necessarily what these regularities should be, but their conjecture was really attractive. They conjectured that if you just look at, again, that partition that's corresponding to that Grassmannian permutation that's indexing that variety that they were studying, they conjectured that the regularity is just going to be some weighted sum, where you're just summing up a weighted differences between the consecutive entries in that partition. But the varieties that they were looking at are also Kazhdan-Lusztig varieties. And in particular, when you apply this map that I was talking about on the previous slide, the vexillary permutation that you get that's mapping to this Grassmannian pair is precisely just a Grassmannian matrix Schubert variety. So using our theorem, we were able to correct their conjecture. So in general, their conjecture is almost always an upper bound, but we were able to correct that using our theorem. And the second application that we have is to allow us to compute regularities of one-sided mixed ladder determinantal ideals. So in previous settings, we were sort of taking, for maybe the classical determinantal variety case, you're taking minors of a rectangular matrix. What if we take minors of maybe a partition shape of indeterminates? And the size of minors that we'll take are dictated by some marked points on the boundary. So let's say if I had marked maybe a 3 there, that would tell me I want to take the 3 minors of that piece of my matrix. And write down your defining ideal that way. In fact, these are, again, vexillary matrix Schubert varieties. So we can, again, write down, use our formula to compute these regularities for these one-sided mixed ladder determinantal ideals. One last thing I want to mention is at the moment I'm looking at extending this to two-sided mixed ladder determinantal ideals. So instead of having a partition shape of indeterminates, having a sort of skew shape of indeterminates. And in this case, these varieties are no longer, you can't recover them as always as matrix Schubert varieties, for example, as our previous results had been using. But I do have partial results in the case for these two-sided mixed ladder determinantal ideals, which appear as Kazhdan-Lusztig varieties indexed by a pair of now 3 to 1 avoiding permutations. But I'll stop here. Thank you.
Okay, great. Many thanks for a very nice lecture. So let's thank the speaker, and we have time for a couple of questions, if any. Okay, so if there's no further questions, then let's thank the speaker again, and we'll resume at 4:20 with the last contributed talk of the day. Thanks.
Thank you.